Then it is time to get started. Okay, so if you remember, last week we ended up extending our definition of functors with monoidal properties. Monoids are these things where we have basically a constructor, the unit. Unit takes as input just a single a and returns f of a. So basically it takes the value a, which may be whatever we want, because the monadic structure is just a wrapped around arbitrary values. It doesn't depend on the values themselves. It's just a definition of a very smart composable box. And we take the value and we put it inside this, let's say, box for now, because boxes are kind of something that speaks to the imagination for now. And join takes as input a box inside the box and just flattens it out into a single box. And yeah, that's kind of it. And as long as f is also a functor, which in this case is required because apply will not work unless f actually is a functor, then we have a monad. So the monad needs to have a functor f, a unit operation, the constructor, and a join operation, which is flattening. A very common method on top of monads is then. Then takes as input an instance of the monad, a function that works on whatever is found inside the box, on the content that the original monad, in our case I called it p, whatever this p carries, and f takes as input whatever p carries and returns an option of b. And of course you can imagine that because p is a functor, then applying mapping p with f leads us to an option of b, which we can then just flatten. And lo and behold, this is exactly what we can do here. We map option f, just wrapped into our function because that's what map option expects. Then, because this leads us to an option of b, then we join, and of course we have to pass p because this then operator needs to return the flattened option of b. And the cool thing about then is that we can use it to create what are called comprehensions, for example. But this is also the very same syntax that we know from the way we deal with promises. And this then is the very same then of promises, but it is also called flat map in, for example, lists. I think also in arrays in JavaScript. It is called select many in link in C#. It is called continue with in the task parallel library in C#, and so on. And working with monads and giving them the then operator, which is always given by mapping and then joining. It doesn't matter which monad it is, this is a universal truth. Then we get a very smart data structure with a very, very, very important operator, then option in our case, that we can use to tackle some of the most complex scenarios ever. And indeed, what we're going to do now is we're going to extend our arsenal. We are going to see today mostly the state monad, and then in the next classes we're going to apply what we learned to the state monad to two real-world, very useful abstractions. The coroutine monad and the react monad. And then we're even going to combine them together. So today we're going to move away from the modeling of a static state, which only defines what things are when they are at rest, and we're going to focus on what things do. We're going to model processes with monadic types. All right, let's consider a process that works on state. Now, the process must be able at all times to, well, read from the state and write to the state. So we could say that a process with a given state is a function from state to state. But this is not enough, because a process can also yield a result. Like if you consider a process as something that, okay, is stateful in a sense, because yeah, you give it a state and it doesn't really change the state, but it gives you back the new state at the end of the computation. Okay, this is clear. But the process is also supposed to produce a result. And that result is not the state. The state is simply the container of all the side effects. So we add another type, A, which is the type of the result. And here we can say that what we actually return is a pair of A and S. So a stateful process takes as input the state, S, and returns, well, the new state together with a result. Sometimes the result will be unit when we want to say that a computation only changes the state. Sometimes the output state will be identical to the input state, because the only thing that the process did was to calculate an A from the state. And sometimes we will get a new state and an interesting value out of it when the process contains computations that both extract a value from the state and also modify the state. How do we do this? Well, as usual, we need a mapping function. Also, it will not really be possible to define monad on top of process, because process is monadic in the A argument, but not in S, because the state S will always remain the same. So it's a little bit awkward to hammer this into our framework, because our framework expects types that only take one type parameter, and here we actually have two. It would be extremely cool to be able to have carry the type parameters, like higher order types, but we don't really, and so that's why we're not going to define something as pretty as we did for the option monad. And for this, I apologize. It would have been very cool. Now, map state. Indeed, it has always this extra awkward argument, the state. Well, awkward but very much needed, but then the actual functorial transformation happens between A and B. We take as input, well, you can imagine, a function from A to B. And what do we return? Well, we return a function from process. Actually, you know what? I will call this a state because this is typically called the state monad, so I will stick to the, let's say, classic name. But it really models a stateful process. And we take a state of S of A into a state of S of B. Okay. And now we can move on to the definition of this thing. Well, we have a function, we take as input the stateful process, P, or P0, the initial one. And, well, now we have to produce a new stateful process. Okay, so what are we going to do? Well, P0 is a state. Actually, you know what? First, let me create this manually. We want to create a state S of B. So what we're going to do is we're going to return this new state of S of B, which is a function. And look, we even get pretty decent intelligence. This says, well, okay, the state that we're creating the process, well, let's define it. Okay, we take as input the state. This is the state that we get. This state, what are we going to do? We're going to feed it to P0, because that's all we have at this point. Like, we have P0, which gives us S of A. And now we are creating this wrapper adapter proxy state of S of B, which will have to be based on P0 and F. And the moment someone tries to run this state of S of B, well, they have to give us a state. Let's call it indeed S0. And now that we have S0, let's say temp will be P0. And, well, this is a state of S of A, so I just call it. Okay, what do I have in temp? In temp I have the first value, which is A, and the second value, which is S. S we can't really do much about, but let's say we have the result. Nah, you know what? Result and S1. And let's kindly ask TypeScript to remove the error. So we see, okay, what comes out of P0 of S0? A result of type A, makes sense, and a value S1 of type S. S1 is the state as P0 transformed it. And this we have to keep. But how do we get, I wonder, to the value of type B? Oh, well, we could say call f of res. And there you go. So what we have done is we have created a state, a stateful process that wraps P0 by running it and intercepting the result, passing it through through F, obtaining the B, and then we also pass through the resulting state. Okay, now if you remember, we did have, oh, did we not have map pair? Let me check if we have pair. Oh yes, we have map to pair. Okay, map to pair, if you remember, it transforms both elements of a pair. So we take as input a pair of AB, two transformations from A to A1 and from B to B1, and then we get a pair of A1, B1. And you could say that what we are really doing here, from res S1 into F of res and S1, is actually invoking map to pair with, well, F, because this is what we do to the first argument, and the identity over S as the second argument. And we could say, well, this we can call back temp, and we can just pass temp. And oh, look, this is working, very good, very good. So you could say, well, just let's remove the temp. Okay, very good. But this thing here actually first runs P0 and then runs map pair. First we run P0, and whatever result of P0, which we know is the pair of A and S, we pass through map to pair. So we can say P0, then map to pair, and of course we have to, well, pass S0 now because we have to run it. But do we have to run it? As a matter of fact, we do not. We can simply say, well, let's just return P0, then map to pair of F ID of S. And this we can get rid of, the curly brackets we can get rid of, and there you go, a very, 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 very elegant mapping function. And if you think about it, it actually makes sense because state is a function from S pair of A of S. So what we say is, okay, run S, and this is the then bit, and then take this value, and okay, we have to map it because we want to keep the second part, but the first part, the A, we want to transform with F from an A into a B. And the useful trick for this is that what I did in the original version was, okay, I need to return a function, so fun. This is a state, and the state on its own is a function from S to pair blah blah. So, you know what? Well, the state. Let's get it. Then I need to return this state, which is a function from S to pair of B of S. Okay, and then I literally remember I said, okay, no, we return a function, and then what's here, S0. So I gathered all the arguments, and this is actually a very legit way of working. And then when you have the working implementation, then you can look into streamlining it and removing as many arguments as possible. So I don't really think there are many people. I mean, I guess there are some brilliant people who can just figure this out in one go. I am not one of them. Usually what I do is first I gather all the structures, like if I have a fun that has to return a state, so yeah, this state is also a fun. I just create all these structures, get all the arguments, see how I can fit them together, because at the most nested point, we saw we had P0, S0, and F. And then there aren't that many things you can do actually, because S0 has to go in P0, and then F can be applied on the first value. There is barely any choice of what you can do, what you can call with. All right. Now, let's define the unit state. Or actually, I will still put it, I will still make it generic in S. Yes, very good. So I'm creating something like this monadic container for the option, but I'm getting the S argument separately, so that I get to define a very similar structure as I had before. Okay, so unit will be a generic type, will be a generic function, and it has to return a function from identity of A into state of S of A. Now, so what do? We build a function, We take as input the value, I will just call it A out of sheer laziness. Now I have to create a state. Very good. So I will create a function that takes as input the state. I will call it as 0. I try to always number the states based on, in this local computation, what time did we get them. Like S0 is the first time, S1 is the second state we get, S2 is the second state, etc. Because it's very easy to get lost into which state is the most recent, so I like to make it very explicit, to number the states sequentially, sort of a long time. Okay. What do I have to return now? Well, I have to return a state of S of A, a pair of AS. I have S, I have S0. There we go. That's the very, very, very simple constructor over states. Now we need join. Okay. Join is also generic, and we need to take a state of S of state of S. The intelligence is driving me crazy. Of A, so a nested state of A, and we need to flatten it into a state of S of A. Okay, now let's take the process within process, and well, what do I have to do? I have to return this state. So what I'm going to do is I say, okay, as I return this state, it's going to be a shell, a dynamically calculated proxy that can extract the ANS directly from PP, and of course S0. Okay, so now I have S0. What do I do? Well, I can feed it to PP. So let's say temp is PP of S0. Maybe PP was not exactly the most genius naming, but we are going to stick to it. Okay, and what is in temp? In temp we are going to find a value of type state SA, because the first process returns a process, but it also returns the new state. So this is a pair of state S of A and S. So we get the nested process, the child process. PP could also stand for parent process. Also cool. And S1, the new state. What do we do now? Well, at this point, because what do we need to return from this whole shebang? We need to return a pair of A and S. And CP applied to S1 will actually return the pair. Of A and S. I guess you are wondering, okay, is there a way to turn this into something prettier? Oh, I'm so happy you asked, because yes, there is a way to turn this into something prettier, and this is called, and this uses apply. So here I have a function and its argument in a pair. So apply takes as input a pair of a function. Oh well, it is generic, of course. Let me move it out. Apply takes as input. Well, of course, two values, input and output. And then it takes as input a pair of a function from A to B and a value A. And what does it return? Well, it returns a B, of course. So we are a function which takes as input the function and the argument, and simply applies the function to the argument. And now what we could say is apply of pair to value. So let's say CP and S1. Is it happy? No, it is not happy. It needs a little bit more of a hint. This is S, and the result is pair of A and S. Yes, oh, so pretty. Okay, so armed with this apply function, unfortunately the ability of the type inference of TypeScript is impressive, but we really are stretching it here. But they will get to it eventually. So now, well, I don't even need to define this value. And I don't even need, actually, all these curly brackets. But you might notice that this is actually simply saying, okay, first you do pp and then you do apply. So we can even skip actually the explicit invocation and the fun s, and there we go. Apply is such a crucial aspect of functions that I will even move it here because it is part of our core framework of functions. We didn't need a utility that applies things over a pair, but when you have the functions and the pairs, you can simply say that apply takes the function and the argument and squishes them together. And we have join state, very pretty, and also very, very elegant actually. And interesting that this basically says, okay, run pp, and then, well, bring together the function that you've gotten because you've gotten a state and the state. So the function that wants a state and gives us the a and s together, and the state that you've gotten by running pp, because pp, the parent process, also is a process, so yields a new state. Let's actually add two utilities. So get state, which takes as input a function of state of s, which is a state of s, and this takes as input a state s0 and returns s0 as a result and the state unmodified as the new state. So get state simply gives us the state itself s0 as the result. It allows us to inspect the state at this point. Set state takes as input a new state of type s and gives us a state of s of unit, because we don't really care about the result of this. What we do is we take as input the state, which we ignore. Then as the new state, well, as unit we give nothing back, but as a new state we give new state. So basically set state replaces the state. And actually, if you really ask me, I also like to define something that takes as input a state updater, because why not, right? So what if I get a state updater, and here I get as input s0, and I invoke the state updater on top of s0? Even better. Then we can set the state, say, okay, here's the new state, and there you go. Or we can say, no, give me the current value of the state, and I will calculate the new value of the state, and then perform a set on that. And yes, we could have also defined this with the map pair, by the way, but we're not going to do it. Okay, so what we're going to do now is we're going to model a tiny little embedded programming language with our state monad. So let's define our memory, our context. This will be our state as something which has a bunch of things. A is a number, B is a number, C is a string, and D is a string. Okay, so we have basically a memory with 4 slots for data. We could also decide that there are some dynamic components, like, I don't know, let's say a sort of heap, which is an immutable map from string to whatever. And yeah, I mean, even to any if we wanted, or a heap, or a bunch of numbers, you know, but at least we say, okay, the name is dynamic, but everything is a number, and then we have the booleans, etc. We can make this extensible, but for now I want to keep it as simple as possible. Okay, and this is our memory, and now I'm going to define a statement or an instruction as that returns a result of type A as a state, so a stateful process in the memory, but with a result of type A. So basically I'm fixing the value memory. So now instruction really is a very proper this is a proper monad, because a state, well, it has 2 type arguments, but instruction only has 1. And what we could do is we could say that instruction is, or just I will, no, ints, because I don't want to write to type too much. And then I call state monad with memory. So I have unit, and I have join, and get state, and set state, etc. Okay. All right. Oh, I was almost forgetting. Well, we definitely need a then state. Oh, very important. It's easy to forget because this thing is completely automated. Well, almost automated. We have the extra argument. We have a state of S of A. F goes from A into a state of S of B. We return a state of S of B, map state, which we have, followed by state monad over S dot join. This is a mild disappointment. Well, let's find out what went wrong. Okay, now. This is a bit of a bummer. Okay, let's find out what went wrong. What I'm going to do, well, first of all, I'm going to get the compiler to not bother us. And then let's take a look at what is this, what is the type of this? Is this what we expect? So temp is state monad join of A. And okay, this takes as input a function from state of S of A into state of S of A. Okay, this is what we expect. Very good. So, well, actually, let's take P and map it. So this will be temp2, and temp1 will be map state of fun F. And what does this want? Oh, perhaps the problem is with map state. Oh, because the S is unknown. So let's say that you go from S of A into state of S of B. Is this correct? Yes. Okay. And then we could take temp1, which is state of it. Yeah, okay. Actually, I think we are covered, to be honest. I'm going to attempt. Oh, still unhappy. Okay, this thing is going to give us a bit of a fight, but such is life. Tempo1. It takes as input the state of SOA and gives us a state of. Oh, of course. Because this is the join of B naturally. So what we are joining is the state of B, not the state of A. Okay, and now it works. There you go. Almost easy peasy. I mean, I was kind of panicking there, but just inside and very, very discreetly. So yeah, there's that. Okay. All right. Now, what we do like to do very often is we actually kind of like to add this monadic then operator to the state itself, because this would make things a lot more elegant. So for now, let's use it without. But let's make it pretty immediately. Yes. Let's make it pretty immediately. So let me see. But a function already does have a then. Oi. Then I will just give it a then state. Let's do it like this. Okay. So then state. Well, we are already in the context of a state of S of A, so we're going to get as input one of these. And then we want to return the state of S of B, and of course this needs to be generic in B. All right. Now, of course, all the places where we're trying to build a state from a function don't work anymore, because now we need a proper state constructor. So, because here, well, we're returning a function, but this doesn't have the then state method, so we have to add it. So state will be the constructor that takes as input given two type arguments, S of A, and an actual implementation, like the actual implementation, which is just a function, and this will return a state of S of A. How do we do this? Well, you might remember we force actual to be of type state of S of A. It's a dangerous operation because, well, we're kind of implying that it has something that it doesn't have, but then we're going to define it. So temp.thenState will be a function which has to be generic in B, takes as input this, which is the state of S of A. Then it takes as input, and this I'm going to copy out of sheer laziness, yes, the function that turns the A into a state of S of B. Then we return the state of S of B, and there is no implementation effort here to be done because we already have the implementation of then state, so we can just call then state with this and F, and it needs, oh, it doesn't even need a little push. Okay, this is very good. Okay, then I can simply wrap this around state. Oh, well, do I need to provide some extra hints? Possibly. No. Oh, this is a legit function, but it's the thing that we get from this then. So let me see. This then takes as input the function. Can I get away with this? No, I definitely cannot. Okay, so no. Okay, I guess it will be worth it at some point. Let's go back to the original definition, because now that we added the wrapper, we are kind of we have to put things in between. Okay, so map state, we return the function that takes as input the state. Then I can return. Let me rebuild it. We have the result and S1, and this is equal to P0 applied on top of S0. Okay, and then I can return the tuple of F of res and S1. Okay, this doesn't work yet, but this is the state that we are wrapping, and there we go. Okay, very good. Now, let's see how far we get in cleaning this up. Possibly a little less than the previous version, but maybe not. Now here what we're going to do is going to be, what was it before? Just a map to pair of f of id of s, which we apply immediately to p0 of s0, so this has made it a tiny little better. And I guess now well, and this will of course be P0 followed by the whole thing, and then apply to S0, and we can remove the S0, and there we are. I do have the feeling that this is something I already attempted and it should have worked, but perhaps I made a mistake in some brackets. Okay, anyway, this thing works. Now, unit. Unit has to take as input the ID of A, so that would be the argument A, and wrap it in a state. Let's try, wrap it in a state. Okay, this works. Here, join takes as input a state of S of A and returns a state of S of A, which I suspect very strongly then is going to be just this. Yes. Get state, well, we just need to wrap the function around the state. Most excellent. Also for set state, also for update state. It's kind of funny that it takes more effort to, in a sense, make things streamlined than to actually build the state monad itself, which is an interesting, I think, psychological bias of developers, because we do really have this tendency to see, to underestimate tedious but complicated tasks like this one, and to overestimate things that are complex, like the definition of the monad itself. So anyway, something to reflect about when learning how to estimate things. Someone had asked me how long does it take to add the then state operator. I would have probably made a huge mistake in the estimate, whereas for the monad, I would have probably said, yeah, that this will take me longer than what it would actually have taken me. Anyway, now that we have our instructions, we can actually start doing stuff. For example, we could say ins dot, well, okay, get state, very good, then state, to disambiguate with then. And what does this give us? Well, it gives us, this is actually very cool, it takes as input the memory, so it gives us the memory, so this is the current state, and now I can do stuff like, I don't know, well, let's set the state to the same memory, so current state, where A is current state dot A plus 1. And then, well, I could say then read the state again. And obviously, whenever you have a get state and set state, you could also say, well, this is not really a get state, set state, but rather an update state. And update state takes as input the updater itself and returns the new state. So let me remove some extra brackets. Oh, and this needs to be an updater. What did we call it? The updater, just needs to be wrapped in function. Okay. Actually, instead of getting an updater, I'm going to just get the lambda here. Yes, I will get the lambda because I don't want to wrap this in an updater. I think it doesn't add a lot to the usability. So this will take as input the current state and gives us the new state back. Yes, okay, so update state here increments A by 1. And after this, then, well, the value we get is unit because it doesn't really matter what we got. So I can even just say then with then state, and this also gets unit because they are very, very similar. And then I can say, okay, now let's increment, how about we increment B? And so on. We can make this even prettier. Let's add to the operations of ins. Let's add something else. So we just get everything that's in ins, but I also want a couple of extra operators because I think those can be very cool. I will define getVar, which well, takes as input one of the keys of memory and returns, well, and of course we also do need the value for the key because this helps with IntelliSense. And what we want to get back is an instruction of memory of whatever key we were given. Oh, of course. Yes. Okay, how do we do this? Now, let's see. Let's do get state first. And then in the then state, we get the current state. and we can simply say, okay, well, we unit, because this is what is going to return a value. What do we unit? Ins dot unit of the current of k. Oh, and here we need to provide, yes, the right type annotation. All right. Of course, we can also set a variable in almost the same way. So let's say that we have a k which extends key of memory, of course. Then we have a value which is the same value of whatever k is in memory. And this is an instruction of unit, because we don't really want to know what happened. We just want to override the variable. Okay, so we don't even get the state. Actually, we update the state. We take as input the current state. And here, what we're going to do is, well, we get current, and we think k becomes v. But I am having oh, yes, okay, this looks good to me. And instead of writing this code here that is a tiny little bit ugly, well, not even that ugly actually, we could have done was ins not get var a, then, and this is the value of a, look, it says it's a, oh, pardon, then state, and the state gets as input the number, the value of a, then I can say ins dot set var, which var, well, a, and here now it knows, okay, we're supposed to get a number, let's say we put a plus 1, then state ins dot get var. Now let's get something else, let's get one of the strings c, then here we get the value of c, ins dot get var d, then we get the value of d, and at this point what we're going to do is we set as a variable c, c plus d. Okay, oh, yeah, it's just automatic for me. But let's see. This seems to be slightly unhappy. State memory unit. Oh, yes, of course. Because after set var, then state needs to get an argument, and that argument is unit, but we still need to get the argument itself. Okay, well, at this point, I'm actually even curious to see whether or not this works. So this is a program. So let's say my program 1, and we can run it. We can say, okay, run my program 1, and of course we need to give an initial memory. So let's say that, well, give a0, b0, c will be c, and d will be d, because then when they are added together, we actually see if the result makes sense. And node out slash index.js, and what we get is a1, b0, c is cd, and d is d. Now, I can't really emphasize how powerful this thing is. A little bit has to do with the type safety of the getting and setting variables, because this is actually quite amazing, but it's very uncommon for most modern programming languages. So here, usual kudos to TypeScript, because I mean, this is really something for which the only reaction possible is chapeau. But also we've built the monad, we've built the composition, we added the then operator, and it all just works out of the box thanks to what? Thanks to the fact that most of these comes out of a framework, the framework of monads, which tells us exactly what do we need to implement, and the hardest function of all, which is then state, yeah, this comes for free. We don't even need to think about this. So I was thinking actually that for today perhaps I think it's enough, to be honest. So, all right, now, so what we have seen today is the ability to define through this process monad our little programming languages within our application. And as they stand now, the programming language we built is just a very small and to an extent useless subset of the programming language we're running into. What we're going to do now, and by now I mean in the next lessons, we're going to extend our little programming language with two things. Actually, three things. Error management, so that we define our own system for managing errors, and that is just to show that we can extend it. Then we're going to add something substantial, which is interruptions. We're going to build processes that can take a break, that can stop without being done, but just saying, okay, I'm done for now, but here's the rest of my calculation. And these are called coroutines or interruptible processes, and these are things that you don't normally have in programming languages. So this is a way to show that through monads, we can extend the programming language to do something that it absolutely cannot do easily out of the box. And then we're going to add a rendering to this. We're going to make it possible for these interruptible processes to be part of a rendering system based on React in our case. We are going to make React functorial, not monadic, because the monadic extension is not very useful because we don't really have this notion of sequence between React components. And we're going to take our interruptible processes and define a translation from interruptible processes into this React functor, so that we have a process like the one we had, with errors, with interruptions, and with the rendering. And when you have that, you have covered a huge lot of computational concepts in one go. Thank you for the following. Thank you for the keeping up. This one was quite tough, but I hope you can see the immense power we're starting to wield. Because defining a little programming language is already quite an accomplishment, and we're not even done. We are going to extend the programming language to grasp, to claim control over the kind of semantics that we need in the domain for which we need to build applications.